Hello. So today we are doing this problem called number of longest increasing subsequence. So the problem says we get a unsorted array of integers and we want to find the number of longest increasing subsequence. So this is just a variation of a problem here called longest increasing subsequence. I have another video explanation of this one on my channel, so you check that out first. Because this one is just a modification of that solution. And so the problem says we want to find the number of longest increasing subsequence. And so whenever you have some kind of counting for a longest increasing subsequence, or for a longest or shortest or minimum or max, that you should immediately think about DP. Or at least a recursive solution, and then apply memoization and then do DP. But for this problem, since I already done the recursive and the memoization solution for the previous problem, I'm just going to jump for the one similar to it. I'm just going to jump directly into a DP solution for this one. And so for this problem, our state is going to be the number of longest. So let's write first the goal which is what we are looking for. So what we are looking for is the longest number of longest increasing subsequence, right? That's what we are looking for. So kind of our state has to be something that from which we can retrieve this result here. So one way we can do that is just number of longest increasing, let's just call them LAS, longest increasing subsequences, ending at some position, right? And so our base case would be number of longest increasing subsequence ending at 0, for example. Yeah, ending at 0, so only the first element. So if we take the array, let's say 2, 6, 3, 4, the longest increasing subsequence ending at 0, that's just one element, so it has to be increasing and it's just one element, so that's just 2, right? And so it's like so the set of them is just 2, right? So that means that this one is only 1, right? And that's kind of the case for every I, right? Because every element ending at position I, you can just take that element alone. And so for all I, we can say that directly dp of I is equal to 1. Okay, I'm going to change this a little bit. I'm going to call this count, which counts the number of LAS, right? But sometimes with DP you need multiple things, right? You need multiple tables to keep track of what you are doing. You can either use multiple things or use a table with 2 dimensions. But in this case, I think it's easier to use one table for each state. And so we can have our state be 2 things here. So one is the number of longest increasing subsequence ending at I, but I also need the length of the increasing subsequence, because if here I find the sequence ending at 6 with length 2, let's say there are other numbers, and here at 3 I can't take 6, so I have to do 2, 3. So that's another longest increasing subsequence ending at 2. And so I need to increase my count at that time. But I need also to know that here we had 1 with length at 0, 1 with length 1, and then at 3 we have 1 with length 2, so that we can know if we need to increase the count, right? And so we need another state, which is the length of the longest increasing subsequence ending at I. Ending at I. So that's an extra thing we need for and this is the one that we used for the previous problem, the one that it was similar to this one, which was this. And so here, let's call this one count of I, and let's call this one dp of I. So that was from this problem, because so Yeah, that's the advanced solution. Okay, that's still not. Yep, so the state DPI, length of the longest increase in subsequence. That's what we use for this problem. Because we are looking for the length of the longest increase in subsequence. And so for this problem, now we need another thing. We need the state and the transition, right? So state or transition actually, or the recurrence, you can call it transition or recurrence. So we know that one other thing that we need to do is we know that dp of 0 ending as the length of the longest increase in subsequence ending at 0, that's also 1, right? And for every, just like with the count, for every number we can just take that element, and so we can just say for all of them dpi also starts out as 1, right? Now for the transition, what should happen? So for every element I, we do, what do we do? So for every I, we check all the j elements before it to be able to identify if with that element we can extend our increase in subsequence by 1, by this element basically. And so we'll check with 2. How can we tell if we can increase? If 2 is less, so basically just by checking if number at g is less than number of I, right? At I, because if 2 is less than 4, which is the case, then that means we can extend 2 by 4. So we know at least without looking at these numbers, we can achieve an LES of length 2, right? And so that means that the count of I here is at least 2, right? The number of those of length 2 becomes 2, right? And the DPI at this point becomes 2, right? And so where did this 2 come from here? This 2 here is just dp of j, which was 1. Remember, because it's one element, so it's plus 1, right? And the dp of, it's the count of g. And the dp of I is just because ending at this position is of length 1, so increasing it by adding this 1 to it, it will make the length become 2, right? So now our length becomes 2. Yeah, sorry, it's actually just equal because we can't say that we have now 2 of length 2, we have just 1 of length 2. But because we had, if we had, like, let's say if we had j as a part of another longest subsequence of length 2, of length 1, it can't. But if it's, let's say it had another subsequence of length 2, then maybe we can have 2 here, right? So it's just equal to this. Now what happens if so we know that this is dp of j plus 1, right? And this is when we do if nim of I, so we need another thing actually, because there are 2 cases, right? So there is one case where, so here we have 2 cases. So one case is that dp of I, so the length of the longest subsequence ending at I is equal to the longest subsequence ending at j plus 1. For example, let's say this length here is 2, and this length here is, so basically dp of I achieved before 1 of length 2. And then with j, it achieves another one of length 2, right? So that means that we can increase the count, because basically what this means is dpi had for example, if we take length 2, that means dp of I had a subsequence of length 2 already. And then now with j, it achieves another sequence of length 2. And so that means that we can say that the count of I is now going to be added to it a count of G, because now we need to add the previous count that we had because the length is the same. So we need to add the new ones that are formed using J, which are just count of J, because every sequence involving J that had a length, let's say dp of I minus 1, we can add our element to it for it to have length dp of I, and so we have as many of those involving J, and so we add those to count of I. And what happens in this case for dp of I? In this case, dp of I will stay the same because it was already the same length, right? Now what happens in the case where dp of I is less than dp of J plus 1? So let's say it was 2, but with J we are able to achieve 3. So at that point, dp of I changes because now the length should be the new longest one, because the definition of dp of I is the length of the longest increase in subsequence ending at I. So we found another one that is longer than the one we had before. So that means we need to update it. And what happens to the count of I? So now the count of I, before it was, let's say, dp of J, the length was less than dp of J plus 1. So let's say dp of J is like 3. And so now the dp of I should become 4, right? And so that means that the ones before that had the count of E, let's say we had 3 longest increase in subsequence of length 2, those don't matter anymore because they are not the longest increase in subsequence, and so we shouldn't count them. And so we should just replace count of I with count of J, pretty much. And so this is our recurrence, right? And if names of J is bigger than names of I, then we can't form a subsequence, so we should just skip that. And so now we have our transition sequence here, 2 cases, and the first one is this. And then after this one, we need to think about how can we retrieve the final result, which is the number of the longest increase in subsequence. So we found for each one of them, and so we need to somehow keep track of the longest increase in subsequence, and then keep track of both its length and how many we have, right? Why do we keep track of its length? So that we know if we have a new longer one, we can replace the count with the new count, right? So we kind of can have 2 things, max length and the result, which is the number of longest increase in subsequence. And so what do we do here? Every time we update this here, we can initialize and check basically if the max of length is, if the current maximum length we found so far is equal to the dp of I, which is the length ending at I. That means we need to add this to our count, because let's say we had 2 previous subsequence ending with maximum length 4, right? And then we found that a new sequence ending at I with length 4. That means we need to add that one to those 4 subsequences that are ending at other elements, let's say. So we need to add them, right? And so that means that our max length is that our result is going to, which counts them, is needs to add how many ended at I with the same maximum length, right? But if the maximum length is less than the dp of I, that means we found a new longer increase in subsequence, so this one no longer is valid, and so our res needs to be replaced with the new count, right? So our result needs to be replaced with the new count, right? So basically, let's go into this in more details again. So let's say max length was equal to 3, for example, and we found our dp of I. Let's say I is 6. At index 6, we found a sequence, a longest increasing subsequence of length. Let's say so if the max, let's say 5, right? So this is 5, right? Ending at index 6. So that means ending at index 6. Let's say 3 actually, of length 3. And let's say we had res equal to 2. So let's say we have we had two longest increasing subsequence ending at indices, let's say, I don't know, maybe 4 and 3, right? And so we have, now we have 2 that have length 3. Now we have this one ending at 6 that has length 3. And so the max length is still correct, but the res needs to be now 2 plus 1, because to count this one, right? So 2 plus 1. But let's say this is in the case where count at 6 is equal to 1. So we have just one sequence ending at 6 with length 3. But if we had two sequences of length 3 that are ending at 6, that means we need to add 2, because now we have 4 sequences of length 3 that are ending at this 6, because the other ones are before 6, because in the order that we traversed, we go for I, we go from 0 to the end of the array, right? Now what happens in the case where, let's say, our max length was 3 and our res is still 2, but let's say our DP of 6 is not like 3, but let's say it was 4 for example, and let's say we have 2 sequences ending at 6 that are of length 4. At this point, what should happen? So this is no longer the maximum length. The maximum length is now 4, and so that means we need to change our maximum length to be equal to DP of 6, so it's now 4, and we need to change our result, because these 2 that are of length 3 no longer count. Now what we want is those of length 4, which are 2, and so it becomes 2, which is count of 6, right? So this is the idea behind doing this. And so that's pretty much it. We have the recurrence, and at the end we can just return this result. And so now we can just write this down, and that's pretty much it. And so what did we do? We listed our goal and what we want to return. We found the states that we need. This could have been done with a 2-dimensional array, but we chose to do it with 2 here to make it more clear. And then we determined our base case, we did the recurrence relation, and we found the final result, the goal that we are looking for. And that's pretty much it. So let's start coding this up. So let's just store length here. Let's initialize our 2 tables. So this one starts out with zeros. This one starts out with zeros too. And then we need to say we need maximum length and the result variables. Those gets initialized to 0, and then we need to go through. And so here we said that the base case is that for all of them to be initialized to 1, right? Because there is one ending at 1 of length 1, right? Ending at each I with length 1. And now we need to go through all j before I. That's what we said here. So that would mean we need to go through for j in range of I, and then we need to check this that we said here, and we need to handle the 2 cases. And so the first one is going to be like this: if we do this. The second case is if then at that point we do these 2. And now that we have that, if it's less, we replace. The next step is to do this max length, determine the max length here. For each I we do that, and so that means we need to do it after the for G loop, which means after we know for sure what DP of I and count of I are, and that would mean same thing. And here I forgot to do something, which is replace. We need to replace what I did here, which is replace maximum length with the new real maximum length, which is DP of I, right? And so And at the end we should return, so at the end like this we should return res, and that's pretty much it. So we need this, and so we go through the array, we go through each I, we set up the base case, we go through all j's before I, we check if it's less j, number at j is less than number of I, which means we can extend the longest increasing subsequence. We check if it's still the same length, we just add the count, and then we check if it's less, then we have a new beta count, and so we replace I with that beta count, and we replace the count with how many we have of this beta longest increasing subsequence, and then we compute the maximum length we have so far and how many of that maximum length we have, and then we return the last one. So that's pretty much it. So max length is this. Yep, max length. Okay, submit. Let's see if this passes. Okay, so that solution passes. There is another way we can solve this by using the a similar solution as we did for the previous problem, where we used the bisection or binary search to find where to insert the element. But yeah, I'm going to leave that to you to check that solution out. But that one is better in terms of time complexity. But for this one, the time complexity here is O of n squared, because we are going here n times, right? And then here at most we go n times. It's a little bit tighter than n, but at most n times, and so overall our solution here is O of n squared, right? And in terms of space complexity, our solution is complexity. We use two O of n arrays, right? And then we use these two variables that are constant, and so these two are O2 of n, and so that's the same as O of n, right? And that's pretty much it. That's the time complexity of this time and space complexity of the solution. The other solution I mentioned can solve this problem with O of n log n solution by using binary search. Yeah, so that's it for this solution. Thanks for watching, and see you next time. Bye.